All right, y'all, this is the Stoich balancing and everything else. I'll leave the answer key down in the description as well as a blank version of this test. Let's go ahead and get started. Which information does a molecular formula provide? So that would be like H2O, and it tells you the number of hydrogen and the number of oxygen. It is the actual number. The simplest is called the empirical, and the number of molecules in a mole is Avogadro's. Types of bonds, you got to know that it's ionic, covalent, or metallic. How many oxygen atoms are present in 0.05 moles of BaOH2, 8 water? Um, so what we're going to do is see that there are 8 oxygens here, 2 oxygens here. There are 10 oxygens per molecule. Well, we know that we have 0.05 moles, so 0.0500 mole, and we can turn that into molecules by using Avogadro's. 1 mole is 6.02 times 10 to the 23rd. And then we know that for every 1 molecule, we have 10 oxygen. When we plug this conversion into our calculator, we find that the answer is A, 3.1 times 10 to the 23rd. All right, how many moles of carbon dioxide are produced by the complete combustion of 7 grams of ethene? Ethene is C2H4. Carbon dioxide is CO2. We have 2 carbons here, meaning we'll need 2 carbons of carbon dioxide. So every ethene will produce 2 CO2. So we do 7.0 grams C2H4. We're going to divide by the molar mass, which is 28, because we get that right here, grams per 1 mole. Ethene, C2H4. We'll then use the mole ratio that we just figured out. For every 1 mole ethene, C2H4, we have 2 mole CO2. So all we have to do is go ahead and plug that into our calculator, and we find that our answer is B, 0.5 moles, which is a possible empirical formula for a substance with MR42. So if we just go ahead and do the molecular mass, this is 12 for the 1 carbon plus 1. That's going to be 13, can't be it. This is 12 plus 2, 1 times 2 for the 2 hydrogen. That's still going to be 14, can't be it. This one is C3, so 12 times 3 plus 1 times 6. Oh, that actually does equal 42. So we would think it's C3H6, but this is empirical formula. It is the simplest ratio. C3H6 in simplest terms, we can divide both by 3 and it becomes CH2. So we have to actually go back and realize, no. It was B, CH2, because that is the empirical formula. What is the coefficient for H plus when the equation below is balanced? Now, normally when you do this problem, you just try and balance it as quickly as possible. 1 lead, 1 lead, 1 nitrogen, 1 nitrogen, 3 oxygens, 1 oxygen plus 1 oxygen, not enough. So maybe you'll put a 2 here, and we'll put a 4 here. And our equation is balanced in terms of hydrogens, oxygens, leads, and nitrogens. But the problem is when we do this, the charge is not balanced. We actually end up with a -1 charge here and a 4 positive charge here. We have a 2 positive charge here. So overall, we have 3 plus and 2 plus. That is not balanced. But turns out if we actually double everything, 2, 2, 8, 2, 2, and 4, that is balanced. Now, you might be saying, how do I know to just magically double all these charges? And then that's actually quite simple. Whatever thing we did had to be a multiple of the coefficients from before, because if it wasn't any multiple of our coefficients of that initial 1, 1, 4, 1, 1, 2, those were the ratios, then our actual atoms would be off. So we honestly just had to keep going. So this times 2, and if that didn't work, we would do it times 3. If that didn't work, we do it times 4 until our charge is balanced, because this is the only ratio where the atoms were balanced. So we're going to find out it's D8. Moving on to number 6. What is the coefficient of HCl when the equation is balanced using the smallest possible whole numbers? This one is not too bad. I noticed 2 chlorine here, so I'll put a 2. And then that will balance out the chlorines, and that will balance out the hydrogens. It's just B. All you had to do is put a 2. Number 7, 0.2 moles of magnesium is mixed with 0.1 moles of hydrochloric acid. Now, I already noticed that I have a 1-to-2 ratio, which means I need 2 times the HCl as I do for magnesium. I actually have 1/2 the HCl. So hydrochloric acid is going to be my limiting reagent, meaning it can't be B, it can't be D. Next, I know that for every 2 HCl, I make 1 magnesium chloride, and I make 1 hydrogen gas. That means that if I start with 0.1 mole HCl as a limiting, for every 2 mole HCl, I make 1 mole H2. I just have to divide that by 2, and I get 0.05. Our answer is C. Moving on to 8. What is the sum of coefficients when the equation is balanced with whole numbers? This one's not too incredibly bad. We just have to go through it as normal. No fancy charges here. I have 1 tin. I have 1 tin. I have 1 sodium. I have 2 sodiums. I'm just going to go ahead and put a 2 there as a guess. We'll see what happens. That means I have 4 oxygens plus 2 oxygens. That's 6 oxygens on this side. I have 3 oxygens and 1 oxygen. Ooh, I'll put a 3 actually here. So now that's a total of 6 oxygens, and we'll see if my hydrogens now balance out. I have 4, so I have 4 hydrogens plus 2, that's a total of 6 hydrogen. I have 3 times 2, that's a total of 6 hydrogen. Cool, everything's balanced. I know I did this a slightly different way. It's kind of like my speed run method. 1, 2, 1, 3. That's a sum of 4, 5, 6, and 7. D. Moving on to number 9. 0.1 mole of hydrochloric acid is mixed with 0.1 mole of calcium carbonate. Well, I have a 2-to-1 ratio, which means, once again, hydrochloric acid is my limiting, because we always need 2 times the amount for this to work. Cannot be B, cannot be D. And how much CO2 will I make? Well, we know that 0.10 mole HCl for every 2 mole HCl, again, using the mole ratio, I make 1 mole CO2. So we're just going to divide by 2. And once again, we're going to get C. What is the sum of coefficients when the following equation is balanced with whole numbers? So once again, I'm just going to kind of do this a very quick way. I notice that I have 2 chlorines and 1 chlorine, so I'm going to put a 2 right there. I notice that in addition, I actually have chlorine here, so I have to go back and say, well, it's not 2. I'm going to need 4 to balance the 2 here and 2 here. All right, well, now I have 4 hydrogens. So I'm going to put a 2 here. And I have 1 oxygen, but now that's 2 oxygens. And our 2 oxygens here, we're balanced. 1, 4, 1, 2, 1. That's going to be 9. What volume of carbon dioxide, CO2, can be obtained by reacting 1 decimeter cubed of methane with 1 decimeter cubed of oxygen? Well, we can actually convert moles and volume to the same because gases take up the same space regardless of what gas it is. So we can actually use the same mole ratio that we use for moles as we do with decimeters. If you need the actual proof for that, you can use the data booklet, which says that 1 mole of any gas is equal to 22.7 decimeters cubed of that gas. So we can do a full conversion with that, or just assume the mole ratio works with volumes of gases as well. So if we start with 1 decimeter cubed of methane and 1 decimeter cubed of oxygen, we see that the higher coefficient is on oxygen, so we need 2 of that. So that means our oxygen is going to be limiting. So I will start with 1 decimeter cubed O2. And for every 2 O2. We have 1 CO2. So once again, we are dividing by half. And for number 11, our answer is A. Another balancing, what is the sum of integer coefficients when propene undergoes combustion? So usually with these, I kind of just go starting with the carbons, 3 carbons here. And now my carbons are balanced out. Hydrogen, I have 6, so I'll go ahead and put a 3 over here as well. Now, I notice that from this, I have 6 oxygens from the carbon dioxide, 3 oxygens from the water. That's a total of 9 oxygens. Or actually, that's single oxygen. 9 oxygen atoms. And I know for a fact that I cannot use whole numbers to get to 9, but here's a little secret. I can use 4.5. And technically, this is balanced. But in a more real sense, I'm not using whole integers. So what I'm going to do instead is to get rid of the 4.5, I will just, and I'll put a 1 there, multiply everything by 2. And so my new coefficients will be 2, 9, 6, and 6. And this will hold the same ratio as 1, 4.5, 3, and 3. But now I have the simplest whole numbers, and then I'll just go ahead and add those up. These make 12 plus 11, which is equal to 23. Answer is D. All right, moving on to the long answer questions. Limestone can be converted into a variety of useful commercial products through the lime cycle. Limestone contains high percentages of calcium carbonate. The second step of the lime cycle produces calcium hydroxide. Calcium hydroxide reacts with carbon dioxide to reform calcium carbonate, as shown by the equation, and then calcium carbonate is heated to produce calcium oxide. Calculate the mass of carbon dioxide produced at STP when 555 grams of calcium carbonate decomposes. So I'm going to start with my given, which is 555 grams of calcium carbonate, 555 grams CaCO3, and I'm going to mass of carbon dioxide. So the first thing I'm going to do is use the molar mass, 1 mole CaCO3, and the molar mass of calcium carbonate is 100.1 grams CaCO3. Now that I have moles, I can use 1 mole CaCO3 is equal to 1 mole CO2. Our equation is already balanced, so we don't actually have to do anything to change that. So I will get 1 mole of CO2, and then I can convert 1 mole CO2 by multiplying by 44.01 grams CO2, and I will get a final mass of 244 grams CO2. Now, you want to watch your sig figs. You start with 5 sigs, you end with 5 sig figs. That's it. Moving on to B, write the equation for the reaction of calcium hydroxide with HCl. Now, honestly, I know a lot of you were confused with this about double replacement, single replacement. It really kind of does act as a double replacement. Ca goes with Cl. So we're going to have CaCl, specifically CaCl2. Then OH is going to go with hydrogen. Now, the most common compound formed by oxygen and hydrogen is H2O. And then all we have to do to balance it is notice that we need 2 HCl. And for that 2, we'll also have a 2 water. And we're done. We're balanced. Now, if you want to get fancy, you can add state symbols into this. So this would be aqueous. This would be aqueous. This would also be aqueous. And water is a liquid. That's a lowercase l. All right, determine the volume in decimeters cubed of 0.015 mole decimeter cube calcium hydroxide needed to neutralize 35.0 centimeters of 0.025 moles. So the first thing we're going to do is actually find how many moles of hydrochloric acid we have. So using this equation, we can find that 0.035 decimeters cubed multiplied by 0.025 mole over decimeter cubed. And this is all HCl. Decimeter cubed cancels decimeter cubed. And we will find that we actually are starting with 0.00088 moles. Now, if we start with 0.00088 mole HCl, and we use our equation above, we know that for every 2 HCl, we use 1 CaOH2. So we're just going to divide by 2 to get 0.00088, or sorry, gotta divide by 2, 4 mole of CaOH. Now we have that many moles, and all we're going to do is divide by our molarity. I'll change colors for this. If we divide by our molarity, 0.015 mole per decimeter cubed, that decimeter cubed will go on the top, and I realize that I get a volume of 0.029 decimeters cubed CaOH2. And this equation right here came from the idea that if molarity equals mole over volume, then volume equals mole over molarity. All right, so that's how I got that. Determine the mass in grams of calcium carbonate produced by reacting 2.41 decimeters cubed of 2.33 times 10 to the minus second moles decimeter cubed of calcium hydroxide aqueous with 1.45 grams of carbon dioxide. So for D, what we really have to first do is just figure out which is the limiting reagent. So we're going to start out by finding moles of calcium hydroxide. Yes, moles of calcium hydroxide by using our volume and molarity. 2.41 times 2.33 times 10 to the minus second is going to get us our mole value because decimeters will cancel out, and that will be 0.0562 mole CaOH2. Once we do that, we can find the moles of carbon dioxide. And we know for carbon dioxide, we have 1.45 grams of CO2. We take 1.45 divided by 44.01 for 1 mole. That's grams. And that gives us a total of 0.0330 moles CO2. You'll notice I am very, very strictly keeping my significant figures. As I go back to my equation up here, we see that calcium hydroxide and carbon dioxide both react in a 1-to-1 ratio to make our product, calcium carbonate. That means because they both react in a 1-to-1, whichever has the least starting moles, that's our limiting. So it turns out our CO2 is limiting. I'm using mole ratios to understand that. From that answer, 0.0.0330 mole CO2. Like we just said, it is a 1 mole CO2 to 1 mole CaCO3 1-to-1 ratio. And then all I'm going to do is go from there and calculate 1 mole CaCO3 is equal to 100.1 grams. That is the molar mass, once again used from the previous equation, CaCO3. Mole cancels with mole, mole cancels with mole, and I get an answer of 3.30 grams of calcium carbonate. So you really have to make sure you carry all those moles through. Now, part E says we have 2.85 grams CaCO3 collected. But what we know is that we should have had 3.30 grams of calcium carbonate. When we divide these values and then multiply by 100, we get what's known as the percent yield. And so using the proper values in this equation, we get 86.4% yield. Moving on to 14. Automobile airbags inflate by a rapid decomposition reaction. One typical compound is guanidinium nitrate, which decomposes very rapidly to form nitrogen, water vapor, and carbon. So, to use the proper chemical equation, NH2, 3, NO3. And they already tell us that we get nitrogen, N2, because it's diatomic, plus water, H2O, plus carbon, just straight up carbon. Carbon's not diatomic. We don't have to do anything. And to balance this out, we have one nitrogen here plus 3 nitrogens. So that's a total of 4 nitrogen. So we need a 2. We notice that we have 2 times 3, 6 hydrogens. So we'll need a 3. And we only have 1 carbon, so we still only need 1 carbon. The oxygens will balance out. There it is. Calculate the total number of moles gas produced from the decomposition. Well, first off, what the heck is a gas here? Well, nitrogen's going to be a gas because nitrogen is a gas at natural conditions. Water vapor, water vapor is going to be a gas because we know the vapor of water is a gas. And carbon is usually solid. That's like soot, what we've learned about in combustion. So with these values known, we know that we actually go from 1 mole solid, 1 mole of reactant to 5 moles gas. 5 moles because I have 2 from here plus 3 from here. And carbon will stay solid. All right, so all I have to do is calculate the number of moles made by 10.0 grams of our reactant. CNH2, 3, NO3. And I do that by finding the molar mass. 1 mole is equal to 122.1 grams. And I will then get an answer for this. And let me just calculate that super quickly. So that gives us 0.0819. And then all we're going to do is multiply that number by 5 because we get 5 moles. And that will give us a final reading of 0.409 moles gas. All I did is multiply by 5 because every 1 mole of reactant makes 5 moles of gas. 1 mole of reactant makes 2 plus 3 moles of gas. All right. Number 15, lignite, a type of coal, contains about 0.40% sulfur by mass. Calculate the amount of mole of sulfur dioxide produced when 500 grams of lignite undergoes combustion. Well, I can use stoichiometry for all of this, but I'm going to actually start out with 500.0 grams lignite. And I'm going to multiply it by 0.0040. And that represents 40 becoming a percent because, or 0.4, because 0.40 divided by 100 is 0.0040. And that will get me 2.0 grams of sulfur to only 2 sig figs because I had 2 sig figs in my percent. And then I will do 2.0 grams of sulfur. And I'm just going to do a regular stoichiometric conversion here, taking the 2 grams of sulfur, dividing it by the molar mass of sulfur, which is 32.07 grams per 1 mole. Then I noticed that in this balanced chemical reaction, 1 mole of sulfur is equal to 1 mole sulfur dioxide, mole, gram, molar sulfur, and I will get a grand total of 0.062 mole sulfur dioxide. All right, moving on to my next one. When heated in air, magnesium ribbon reacts with oxygen to form magnesium oxide, and we have all this data here. Let's just start out with A, write the balance equation for the reaction that occurs in the crucible between magnesium and oxygen. Mg plus O2, because it's diatomic, is going to produce MgO, magnesium oxide. Now I do have to balance this, so I'm going to throw a 2 in front of the MgO and a 2 in front of Mg, and I'm done. If I want, I can add some state symbols, solid, gas, solid. And those you kind of just memorize. Oxygen's a gas at room temperature, hence the fact that we can breathe it. State the block of the periodic table where magnesium's located. If we look at our periodic table, magnesium's kind of like right here, which this is the S block. All right. Calculate the amount of magnesium in mole that was used. Well, we can just do some subtraction. 53.726 minus 47.372. So we'll just go ahead and actually take those amounts right there, and we'll write 53.726 minus 47.372. And whatever that number is, that's going to be our total grams. And I'm just going to speed things up a little. Grams mg, and then from that conversion, I will just divide that by the molar mass of mg, which is 24.31 grams mg to 1 mole. And actually, I'm going to do that math right now. This will become 6.354 grams. So we're going to take 6.354 grams and divide it by 24.31. We will get a total of 0.2614 mole magnesium. And I still have 4 sig figs because I've been carrying those through. Assume the reaction is the only one occurring and it goes to completion, but some product has been lost from the crucible. Deduce the percent yield of magnesium oxide in the crucible. So this one's a little more complex. What we're going to actually have to do is see how much we would have produced. And so we're going to do a little bit of stoichiometry for this. So as we move forward, we're going to start by writing our previous answer from before, what we started with, 0.2614. Now, from that, we're going to do our stoich. This is mole mg. I know that for every 2 mole magnesium, 2 moles magnesium, I make 2 mole magnesium oxide. And for every 1 mole magnesium oxide, I have a mass of 40.31 grams magnesium oxide. And that is just our mass of each of those, 24.31 plus 16.00. So doing this stoichiometry, the 2 cancel 2, mole magnesium, mole magnesium, mole magnesium oxide, cancel mole magnesium oxide. I get a total of, I should have 10.536 grams. That's too many sig figs. 10.54 grams. Trying to keep my sig figs consistent. MgO. That is how much MgO I theoretically could produce. So with that in mind, we have to then look at our data. We can see that the mass of the crucible lid after heating is not as much. So what we're going to do is take our 56 minus our 47. Well, it's a much longer number. 56 point, now I have to go back and forth, 941. 941 minus 47.372. And we get an actual value of 9.569. 9.569 grams magnesium oxide. And I'll divide that by my original value, 10.54. I'll multiply by 100, and I will get approximately 91%. I'm not keeping sig figs here. Apologies. All right. Calculate the coefficients that balance the equation in the following reaction. So this is a separate equation, but I'm going to actually start with, I'm going to use my traditional method, Mg, and whoops, Mg, N, H, and O. I have 3 magnesium, 1 magnesium, 2 nitrogen, 1 nitrogen, 2 hydrogen, 3 plus 2, 5 hydrogen, 1 oxygen, 2 oxygen. So I'm going to multiply this one by 3, see what I get. that's going to increase my oxygen and hydrogen values. So hydrogen is now going to be 6, 7, 8, 9 hydrogen. Oxygen is now going to be 6 oxygen. Nitrogen, I'm going to multiply by 2. When I multiply by 2, that's going to change my hydrogen values to instead be 6 plus another 6, 12, right? To go from 2 to 12, I have to multiply by 6. And that's going to change my oxygen value to 6. So my coefficients are 1, 6, 3, 2. All right. Moving forward to number 17, the periodic table gives us information about electron configuration. So we're going to start using some of this and physical and chemical properties of elements. Argon has 3 naturally occurring isotopes. Isotopic composition of sample is 34% 36, 0.06% 38, and 99.6% 40. Calculate the relative atomic mass, giving your answer to 2 decimal places. Cool. We don't have to do the sig figs ourselves. I will take the masses, 36, times their percent abundance, 0.0034, plus 38 times 0.0006, plus 40 times 0.996. So it's going to be relatively close to 40, and we find out that it's 39.99. So that is the relative atomic mass of argon. State the full electron configuration for cobalt-2 ion. I'm going to pull up the periodic table for this one. So cobalt is right, cobalt's right here. So I'm going to go through 1s2, 2s2, 2p6. Let's start by writing that out. 1s2, 1s2, 2s2, 2p6, 3s2, 3p6, 3s2, 3p6. Gonna move my table over a little. Then I'm here at 4s2 and 1, 2, 1, 2, 3, 4, 5, 6, 7. 3d7. All right. That is cobalt 2 plus. But no, that's incorrect. That's not cobalt 2 plus. That's cobalt 2 plus means we have to lose, whoops, that's not how you spell that, lose 2 electrons. Now, the wild thing is the D likes to be the 5 or 10. It doesn't actually like to be removed, but also because of this, generally we think about removing from the higher energy level first. So we're kind of stuck between removing from 4 or 3. In this case, you're just going to remove from 4 actually, so we're going to lose that in our new one. It's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 3d7, because we're going to lose from the 4. Honestly, when in doubt, take from the 4 before the 3. Take from the higher energy level. It'll get you the right one 90% of the time. Okay, ground state electron configuration for iron. It's pretty much the same as cobalt. From the start, the only get-go is now it says ground state instead of full, which means we can cheat and just start at argon. And then we don't have to go all the way up to 3p6. We can just go argon 4s2, 4s2, 3d6. Oh, but wait, it's 2 plus. We're losing 2 electrons. And so the way we lose those 2 electrons is we'll lose 1 from here. And then the d orbital will once again try and remain full. So we'll lose our second one from here. And we'll just say argon 3d6. Lose from the 4 before the 3. That's the general good rule of thumb. All right. Moving on to these mass spec. Show how a relative atomic mass of 63.62 can be obtained from this mass spectrum. Well, I see that 63 has a percent abundance of, right there, 69%. 65 has a percent abundance of 31%. Well, we've been doing this before, so we're just going to do 0.69 times 63 plus 0.31 times 65. Turns out that equals 63.62. You're done. Last problem. Ammonia, NH3, is industrially important for the manufacture of fertilizers, explosives, and plastics. Draw arrows in the boxes to represent the electron configuration nitrogen. Nitrogen has 1s2, 2s2, 2p3. So 1s2, 2s2, 2p1, 2p2, 2p3. We fill them out all up arrows, then lower arrows. So that's it. That is this whole test. Hopefully this helps you. Have a great day and good luck.